If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. In this video, we're going to talk about the curse of dimensionality, a very important topic in data science. But this topic is a little tricky, and that's where I would be needing some company with me. So let me introduce you to some of the guests present with us today. These are the cute guests that we have. If you've struggled to understand this topic earlier, we can assure you that we're going to make it a fantastic and perfect video for you. Let's get started. So let's say you're trying to teach a computer how to differentiate between a cub and a kitten. Of course, it's something which is a common sense for us human beings. We can just look at the object and figure out what it is. But how would a computer be able to differentiate? The computer would be able to differentiate it with the help of features. These features are also called dimensions. Generally, when you have a data, the rows and columns together are called dimensions. But when we talk about dimensionality or dimension reduction, we are talking about columns as our dimensions. So what could be the features to solve this specific problem? Let's list down a few. We could be talking about fur. We could be talking about rosettes. We could be talking about eyes, nose, whiskers, ears, tail, paws, habitat, and behavioral aspects. Now, while all these features are meaningful while differentiating between a cub and a kitten, but for the specific example that we are taking up, green represents the color that is supporting the strongest features. Blue is the color that is taking up not so good features, but not so bad features, kind of okayish. And the color black would be difficult features that will help us differentiate between a cub and a kitten. We cannot rely on these ones too much. So let's talk about each of these one by one. Fur. Generally, the fur in case of a cub would be more coarser and dense, whereas for a kitten, it'll be softer. Rosettes. If we talk about these spots that you can see here, you would be able to very clearly identify that this is definitely not a cat. A cat does not have these rosettes. Next is eyes. They say eyes of a cat are more round, but in this case, you probably will not be able to differentiate just with the eyes. Nose. They say nose is something that's broader in case of a cub compared to a kitten. So this is again a feature, but not a very strong feature maybe. Whiskers. Again, whiskers you may be able to compare, but in this case, just looking at the whiskers, you may not be able to differentiate between a cub and a kitten. Next comes the ears. Now, this is a very important feature because kittens would generally have triangular pointed ears, whereas the cubs would have the rounded ears. So you see a strong point to differentiate. Tail. Now, it could have been a strong feature, but unfortunately, in this particular case, the tail for the cat is not even visible. It's generally more fluffy compared to a cub, but we don't even have it visible, so we can't rely on that feature much. Then it comes to paws. Paws for a cub would typically be bigger compared to a kitten. Habitat, we're marking it black because we don't even have a background here. Yes, it could have been an important feature because generally the images of a cub would have a natural habitat, whereas the cats would be found more in a domestic environment. But since we don't have that here, we can't rely too much on that feature. And the last is behavioral aspect. We can't do much about it in this case because we do not have a video. We are looking at these static images. So if you see, we listed down 10 features, of which, let's say 2 features, rosettes and ears, turn out to be more important. Fur, nose, and paws turn out to be kind of okayish features. And then we have not so important features like eyes, whiskers, tail, habitat, and behavioral. So we had a data which was 10-dimensional, but to be able to solve this specific problem, probably we can do that very confidently by using just 2 features, or maybe if we include some of the features color-coded in blue, that'll be sufficient. We don't need half the features. So why do we call it curse of dimensionality, and how does it even matter? Let's understand that first. First is, if you have more features than what you need to solve a specific problem, you are going to increase the computational complexity. When we talk about real-world datasets, images, and text, we do not have just 5 or 10 features, we have few thousand features. So having more features than what we need would increase the computational complexity, and that also comes with a cost. When you process such data on your machine, or let's say over the cloud, you incur some kind of costs. Cost could be in terms of what you pay the cloud service provider, could also be the amount of time for which your machine is occupied and cannot do anything else. So that's one. Second is, it has an effect which is known as diminishing returns. Now, what is this? So let me show you another example. Let's say we tried to solve a regression kind of a problem where we took features anywhere from 2 to 25. So we took the performance of different models over a range of number of features. Now the y-axis here represents the error and x-axis represents the number of features. Now you can see when we only use 2 features, we had certain amount of error. When we increase the number of features to 3, the error reduced. When we increased to 4, it further went up a little bit. When we took it to 5, the error is the lowest. Now if we are taking it beyond 5, it kind of varies, but obviously it's not better than what we have at 5. So the error that we're getting is lowest at 5. Then why would you use 25 features when 5 features give you the lowest error or the highest accuracy? That's the point. So taking features beyond a point would not improve or enhance the model's performance. It will only increase the complexity of the model and could also lead to some other problems like overfitting, etc. So by now we understand that we do not want to carry extra load or features which do not add value. Then how do we actually go about performing dimension reduction? So there are 2 broad approaches here. First is feature extraction and the other is feature selection. And there are different techniques that support these. For example, for feature extraction, you can use PCA or principal component analysis, LDA or linear discriminant analysis, or even t-SNE, which is a stochastic neighborhood embedding based approach. Similarly, for feature selection, you can use Lasso Regression, and you even have some specific modules. If we talk about Python, in the scikit-learn library, we have a specific module called feature selection, which helps us choose the features. The main difference is feature extraction would transform the feature space. It transforms the entire data explicitly or implicitly. But feature selection would select a subset of actual features, the original features, from the overall data. So it keeps the features in the original form intact, does not transform them. That's the broad difference. Oh, I just realized we forgot that we have some company with us. We have 2 guests with us, the cub and the kitten. Let's do a panel discussion. So the cub has a question. Where can I learn more about dimension reduction? The kitten says, check the links in the description. So the fact is that all these topics that we just mentioned, from PCA to scikit-learn's feature selection module, have been covered in depth in our tutorials and they are available in our playlist. We'll provide you the links in the description. If you really like the way we introduce this complex topic to you in the simplest way, you shouldn't forget to like, share, and subscribe. That's the only ask that comes from me as well as my guests today. Thank you.